Want to design a content delivery network architecture that rivals Netflix or Amazon? In the next few seconds, we'll break down how to build a lightning-fast CDN system.
Imagine a global e-commerce site facing a sudden surge in traffic. Users worldwide experience slow loading times and frequent timeouts. Images and videos take ages to load, leading to abandoned shopping carts and frustrated customers. A CDN, or Content Delivery Network, solves this by strategically distributing content across multiple servers globally. These edge servers cache content closer to users, minimizing latency. Think of it as bringing the data closer to the customer, no matter where they are. This improves website speed and overall user experience dramatically. At its core, a CDN consists of origin servers, which store the original content, and edge servers, which cache copies of that content. When a user requests content, the CDN intelligently routes the request to the nearest edge server. If the content is cached, it's delivered directly to the user. If not, the edge server fetches it from the origin and caches it for future requests. Let's delve into the key components in more detail. First, we have the origin server, which acts as the single source of truth for all content. It could be a web server, a database, or a cloud storage service like AWS S3. The origin server must be highly available and scalable to handle initial requests and updates. Second, we have edge servers, which are strategically placed around the globe. Now that we've covered the origin server and edge nodes, let's explore how content is delivered. When a user requests content, the CDN intelligently determines the closest edge node to serve the request. The process begins with DNS resolution. The user's DNS server resolves the domain name to the CDN's Anycast IP address. Anycast ensures the request is routed to the nearest CDN node, leveraging network routing protocols to find the optimal path. If the edge node has the requested content in its cache, it serves the content directly to the user. This is a cache hit, resulting in very low latency. In the event of a cache miss, the edge node retrieves the content from the origin server. This is a slower process, but it ensures the user always receives the requested content. Once retrieved, the edge node caches the content for future requests, improving performance for subsequent users. Building upon the edge node's content retrieval, efficient routing is paramount. Anycast routing ensures users are directed to the nearest available edge node. This minimizes latency and improves the overall user experience, reducing average load times by 30%. Now let's explore caching strategies. Content is cached at multiple layers, including browser, CDN edge nodes, and origin servers. Cache control headers dictate how long content remains cached. Compression techniques are essential for reducing content size. Brotli compression offers superior compression ratios compared to gzip, decreasing file sizes by an additional 20%. Finally, let's consider security. SSL/TLS termination at the edge node reduces the load on the origin server by offloading encryption and decryption processes. This improves performance and security, decreasing latency and safeguarding content. Building upon SSL/TLS termination at the edge, let's delve into routing strategies. Efficient routing is crucial for directing user requests to the nearest and most optimal edge node within the CDN. Anycast routing is a key technique here, advertising the same IP address from multiple geographical locations. This allows requests to be routed to the closest node based on network proximity, minimizing latency and improving user experience. Consider this: a user in London accesses content. While Anycast handles initial routing, dynamic load balancing within the CDN ensures even distribution of traffic across edge nodes. Consistent hashing algorithms are employed to map content to specific cache servers, minimizing cache misses and maximizing efficiency. If an edge node becomes overloaded or unavailable, traffic is automatically rerouted to the next closest healthy node, maintaining high availability. Consider a scenario where the London node experiences a spike in traffic. The load balancer intelligently distributes requests to nearby nodes, preventing overload and maintaining performance. To enhance efficiency, CDNs utilize a hierarchical caching system. Edge nodes serve content directly to users, while regional or origin caches store less frequently accessed data. When an edge node misses content, it retrieves it from the regional cache, reducing the load on the origin server. This multi-layered approach optimizes content delivery and minimizes latency. Consider a popular image being accessed repeatedly. The edge node caches it, serving subsequent requests directly. Less popular content is retrieved from the regional cache only when needed, reducing stress on the origin server. Furthermore, CDNs often employ asynchronous processing for tasks like log analysis and content invalidation. Message queues such as Kafka decouple these processes from the core content delivery path, improving responsiveness and scalability. For example, when content is updated, an invalidation message is sent to the queue. Worker services asynchronously process these messages, updating cache metadata across the CDN. This ensures that updates are propagated efficiently without impacting real-time content delivery. Now that we've established edge node caching and hierarchical structures, efficient request routing is crucial. CDNs leverage Anycast, directing users to the nearest available edge server. Anycast relies on BGP, broadcasting network prefixes to multiple locations. Building upon efficient routing, CDNs also employ advanced compression techniques. While gzip is widely used, Brotli offers superior compression ratios, reducing file sizes and bandwidth consumption. Brotli leverages a dictionary-based approach, finding repeated sequences. This lowers transfer times, improving website loading speed, and reducing costs for content providers. To maintain high availability and fault tolerance, CDNs implement robust monitoring systems. Edge nodes are continuously monitored for performance and availability. If an edge server fails, Anycast automatically reroutes traffic. Security is paramount for CDNs, protecting content and users from malicious attacks. SSL/TLS termination at the edge offloads encryption processing from origin servers, improving performance. Web application firewalls, WAFs, filter malicious traffic, preventing attacks like DDoS and SQL injection. Building upon efficient routing, CDNs also employ advanced compression techniques to minimize content size and accelerate delivery. Brotli, a modern compression algorithm, consistently outperforms gzip, offering smaller file sizes and faster decompression, thus reducing bandwidth consumption and improving user experience. Building on the compression techniques, another crucial aspect is minimizing latency. HTTP/3, leveraging QUIC, solves the head-of-line HREL blocking problem inherent in TCP-based protocols. By enabling multiple streams to operate independently, HTTP/3 avoids delays caused by packet loss, resulting in lower latency and faster content delivery. To maintain high availability and fault tolerance, CDNs implement robust monitoring systems that continuously assess the health and performance of edge nodes. These systems track key metrics like latency, error rates, and throughput, enabling proactive identification and mitigation of potential issues, ensuring uninterrupted content delivery. Security is paramount for CDNs, protecting content and users from malicious attacks. SSL/TLS termination at the edge nodes reduces latency by decrypting traffic closer to the user. Building upon the security measures, scaling a CDN involves strategic content replication across geographically diverse edge nodes. To handle peak traffic efficiently, CDNs employ dynamic scaling techniques, automatically provisioning additional resources based on real-time demand. This ensures consistent performance and availability, even during unexpected spikes in user activity. Content is strategically placed closer to users, reducing latency and enhancing the overall user experience. To optimize scaling, CDNs leverage consistent hashing for content distribution, ensuring uniform load across edge servers. Consistent hashing minimizes cache invalidation and redistribution, improving cache hit rates and reducing origin server load. Furthermore, CDNs utilize various caching strategies, including LRU, least recently used, and LFU, least frequently used, to optimize content retention based on popularity. Monitoring a CDN is crucial for maintaining performance and identifying potential issues. CDNs implement robust monitoring systems that track key metrics such as latency, throughput, error rates, and cache hit ratios. These metrics provide valuable insights into CDN performance and help identify bottlenecks or areas for optimization. Real-time dashboards and alerts enable CDN operators to proactively address issues and ensure optimal performance. In summary, designing a CDN involves strategically distributing content across geographically diverse edge nodes. Key considerations include optimizing caching strategies, implementing robust security measures, and leveraging dynamic scaling techniques. Effective monitoring and proactive issue resolution are essential for maintaining optimal performance. By carefully addressing these aspects, CDNs can deliver content efficiently and reliably, enhancing the user experience and ensuring high availability.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.